This lesson is intended as an auxiliary lesson attached to the series Three-Dimensional Solids. And in this lesson, I'm going to show a derivation for the formula of the surface area of a frustum. And the first thing we'll talk about is what is a frustum. A frustum is a section of a cone. If you take a cone and slice off the top, you'll have that truncated shape with a flat base on both sides, circular bases, and this is called a frustum. Now, to start talking about the surface area of a frustum, we need to talk about the lateral area of the frustum. And the formula for lateral area of a frustum is based off of the formula for lateral area of a cone, which is pi RL. So this is actually the area of a sector of a circle. If you were to take the net of any cone, the net of the lateral area of the cone has the shape of a sector of a circle. And the area of that sector is pi times the radius of the cone itself times the slant height of the cone. In this case, pi RL. So this entire sector is pi RL. If we want to take a look at the lateral area of the cone, this top cone has the lateral area equal to pi times r, which is x, that's the radius of the cone on top, times the slant height, which is this L minus this Z. So it's L minus Z. So the area of this little sector up here is pi x times L minus Z. Therefore, the area of the frustum, the lateral area of the frustum, here, this lighter colored area, is the area of the lateral area of the entire cone, this whole cone here, which is pi RL, minus the lateral area of the top cone, pi x L minus Z. And that's going to form the basis for our formula. Hopefully you can see that these dimensions have been broken up into similar triangles, similar right triangles as it turns out, where this triangle is similar to this triangle, which is similar to the overall triangle here. And the heart of the formula, the heart of this derivation, is which proportions you use to create the relationship between this side and this side of these two triangles. So that's where we're going to start. And what we're going to do is we're going to use the relationship between the slant heights and the radii of these cones. So the relationship is going to be this slant height is to this slant height as this radius is to this radius. And this gives us our first relationship. So this proportion is what everything is based off of. And the first step we're going to do is we're going to multiply both sides by x and both sides by L minus Z. And that gives us Lx on the left, L times R minus R times Z. Now, one of the critical things to realize here in this derivation is the fact that in our final result, having any terms with this L in it is going to be useless to us because we're not going to have this entire slant height up here. That's all we're really going to have is this Z value, this X value, and this R value. So it's going to be critical for us to get rid of any expressions in terms of this L slant height here. So here we have two of them. So we're going to have to put this in a form where we're solving for L. Now, one of the other very critical elements is the fact that I'm going to have a result that has R minus X in it. This piece here is going to be a crucial factor as we substitute in here and in here for this slant height. This L is going to go away, and we're going to need to replace it with something that's going to give us an R minus X in it, as opposed to an L minus Z, because again, this L minus Z doesn't exist in the final frustum. So we're only going to be able to use these elements that you see in this area here. So that's what our goal is. And to do that, I'm going to rearrange these terms a bit. Now here you see I added the RZ to both sides and then subtracted LX from both sides. And what that does is it gives us RL minus LX, and here we're going to be able to factor out the slant height L, and we'll have the term R minus X, which is this guy over here, and that's what we're looking for. So here we have that factored out, and now the only remaining piece is to solve for the slant height L, so that we can do a proper substitution into this formula, which is going to be our lateral area for the frustum. So I'm going to go ahead and divide both sides by R minus X. And here we have the final form of our original proportion. And this is going to be used to substitute into this formula. So let's go ahead and bring this formula back. And what we're going to do is substitute in for this L, this expression for L. And here you can see that substitution. We substituted RZ over R minus X for this L and for this L in here. And now it just becomes a matter of algebraic manipulation to get this in a cleaner form. First thing, I'm going to take this term here and I'm going to multiply these terms together. And here we can see we have pi times R squared, the R times R is R squared, times Z over the R minus X, and I left this right term alone. Now to simplify this term, what I'm going to do is the old algebraic tool of multiplying this denominator times this numerator, this denominator times that numerator, and this denominator times this denominator to give us a common denominator, one term with a common denominator. And here you can see that 1 times RZ is RZ, R times negative Z is negative RZ, negative X times negative Z is positive XZ. So it's this times this times this with this sign, and then this times this. So 1 times R minus X is this guy. Now you can see that RZ minus RZ causes these two terms to cancel out. And I'm just going to do a quick regrouping of these two terms to get this numerator into this one. And now you see we have two terms with the same denominator. So I'm going to go ahead and combine these two numerators. And here we have pi R squared Z, which is this term, and pi X squared Z, the X squareds combine, over the common denominator R minus X. At this point, hopefully you can see the idea that was involved here. Now, in these two terms here in the numerator, we have a common pi and Z. If we were to factor those out, we'd have an R squared on this side and an X squared on this side. And that would give us the difference of two squares. And that's going to affect this denominator here. You can see we factored out the XZ, and here is our difference of two squares. And this difference of two squares is going to factor into R minus X, R plus X, and that's going to give us a cancellation opportunity with this guy. Now when we cancel out this R minus X, you can see the reason why we had to have this term expressed with an R minus X in the denominator. It's because of this cancellation here, which is going to give us the final form of the lateral area of our frustum. And here it is. So the bottom line is the lateral area of a frustum is pi times the slant height of the frustum, this piece here, this Z, times the sum of the radii of the bases of our frustum. So we'll call this radius the radius of the original cone. That's B1, and this one is the radius of B2. So this is base 1 here, this is base 2 here. And so the lateral area of a frustum is pi times slant height times the sum of the radii of the bases of the frustum. And as a final step, to get the surface area of the frustum, you simply add the areas of the bases of the frustum. And so big B1, area of base 1, is pi R squared. Big B2, area of base 2, is pi X squared, which is that radius. And finally, the area of the frustum is lateral area of the frustum plus area of base 1 plus area of base 2. I hope you found this useful, and I will talk to you in the next video.